Hello. So in this lecture, we're going to study about the existence of limit of a function at x is equal to a. And also we're going to learn how to evaluate left hand limit and the right hand limit of the function. If the left hand limit of the function at a is equal to its right hand limit at a, then we can say that the limit of the function at x is equal to exist. Otherwise, it does not exist. Okay, in other words, we can say that the limit of the function at x is equal to exist if and only if the left hand limit is equal to right hand limit. Okay, so that's the condition of existence of limit of a function at any value. We don't have to every time evaluate left hand limit and right hand limit, because if the function is a single definition function and it's well defined and continuous at given value, then we can just find its limit x tends to a f of x, which is equal to f of a, right? For example, limit x tends to 0 cos x. Now if you substitute 0 is equal to 1 and cos x is continuous and defined at 0, so we are not getting any indeterminate form. Also, if let's say x tends to 1, it's x plus 1 or x squared plus 1, or you can say x plus 2 over x squared plus 1. So it's going to be 3 by 2. So it's a single definition function and it's defined and continuous. Because substituting 1 in this function, we are not getting any indeterminate form or 0 by 0. So the limit of the function can be written in this way. Okay. Now let's see a function where we have to find where we have to evaluate left hand limit and the right hand limit. So let's evaluate left hand limit and the right hand limit for the function x minus 4, absolute function, over x minus 4, where x is cannot be equal to 4. Okay, right? And it's 0 if its x is equal to 4. And we'll find its LHL and RHL at x is equal to 4. Right? Let's first find its left hand limit. So there are certain steps to find left hand limit. So suppose it's a function f of x and we want to calculate its left hand limit at a. So what we'll do, we'll first substitute x tends to a to h tends to 0. We'll substitute here x tends to a from the left side to h tends to 0, and we'll write f of a minus h. So here a is 4, and what is h? H is infinitely small positive real number. It's infinitely small positive real number, right? So here its limit x tends to 4 from the left side, f of x, and we'll write here, instead of x tends to 4, we'll write here h tends to 0, and this is going to be f of 4 minus h. So its limit h tends to 0, and it's going to be 4 minus h minus 4 over 4 minus h minus 4. Here we can cancel out 4 in the numerator and the denominator. So it's going to be limit h tends to 0, it's negative h over negative h. Absolute value of negative h is positive. So it's going to be limit h tends to 0, h over negative h, which is negative 1. So its left hand limit, it's negative 1. Now let's calculate its right hand limit. Let's evaluate its right hand limit. For right hand limit, if the function is limit x tends to a f of x, then we substitute x tends to a to h tends to 0, and we write a plus h. So instead of x, we write here a plus h. Now here in this function, a is 4. So we're going to write limit h tends to 0 f of 4 plus h. Again, h is infinitely small positive real number. So it's going to be limit h tends to 0, 4 plus h minus 4 over 4 plus h minus 4. Here we can cancel out 4, and the both h will be positive and it's going to be positive 1. So here the right hand limit is 1 and the left hand limit is negative 1. So obviously left hand limit is not equal to right hand limit, and so we can say that limit x tends to 4 f of x does not exist because its left hand limit is not equal to right hand limit. Okay, I hope you understood the algorithm of finding left hand limit and the right hand limit of the function. Let's see another question which is not a single definition function. So we wish to calculate its LHL and RHL, and we'll also check its existence: x minus 3, x plus 1, x minus 3 if x is smaller than 2, and x plus 1 if x is greater than 2. Let's first evaluate left hand limit. For okay, we have to find its limit at x is equal to 2. So when we are evaluating left hand limit, it means it's slightly less than 2. It means it should be less than 2. So limit x tends to 2 from the left side. F of x is limit x tends to 2 from left, x minus 3. See, this is here, it's not giving us any indeterminate form if we substitute the value. So we can just write 2 minus 3, which is negative 1. So we can say that its left hand limit is negative 1. And let's now evaluate right hand limit, which is limit x tends to 2 from positive side. If x is greater than 2, then it should be x plus 1. Now here if you substitute with 2, we getting 3. And right hand limit is 3, but the left hand limit is negative 1. So the left hand limit is not equal to right hand limit, and therefore limit x tends to 2 f of x does not exist. Okay, now let's move to question number 3. Here its limit x approaches to 1. That's x plus 1 if x is smaller than 1, and it's x square plus 1 if x is greater than 1. So first we're going to evaluate its left hand limit, which is limit x tends to at a, x is equal to a. At x is equal to a, we'll find the left hand limit and right hand limit. So it's x tends to a from the left side, f of x. So it's just less than 1. It means if it's less than 1, we'll write here x plus 1. X plus 1 is a single definition function. So we're going to just substitute the value of x, which is 1 plus 1, which is 2. So its left hand limit is 2. Now let's see its right hand limit. So if it's greater than 1, then it should be x square plus 1. And here also we're going to substitute, this is 1 plus 1, which is 2. So we can see that left hand limit of the function is equal to right hand limit, and therefore the limit x tends to 1 f of x exists. Okay, so we saw that if left hand limit and the right hand limits are equal, then the limit of the function at a exists, otherwise it does not exist. Let's solve another question, which is f of x is equal to square root of x minus 4 if x is greater than 4, and 8 minus 2x if x is smaller than 4. We need to check its existence at x is equal to 4. So first we're going to evaluate its left hand limit, where x tends to 4 from the left side, f of x. So when it is less than 4, so it's going to be limit x tends to 4 from the left side, it's 8 minus 2x. And it's not giving us any indeterminate form, so we can just substitute. It's going to be 8 2 times 4, which is 0. So the left hand limit for the function is 0 at x is equal to 4. Now we evaluate its right hand limit, which is limit x tends to 4 from positive side, and it's going to be, if x is greater than 4, it's going to be square root of x minus 4, and which is 4 minus 4, which is 0. And here we can see that left hand limit and the right hand limit are equal, they both are equal to 0. So we can say that right hand limit is equal to left hand limit, and therefore the limit x tends to 1 f of x 4 f of x exist. All right. Question. And here we have to prove that the limit x tends to 0 modulus x over x does not exist. And you know that if it does not exist, it means its left hand limit and the right hand limit are not equal. Let's evaluate its left hand limit. Here its limit x tends to 0 from the left side. So we are going to substitute x tends to 0 from the left side to h tends to 0. And we're going to substitute x to a minus h. It means 0 minus h over 0 minus h. So h tends to 0 is going to be h over negative h, which is going to negative 1. So its left hand limit is negative 1. Let's evaluate its right hand limit. X tends to 0 from the right side. And here we're going to substitute x tends to 0 to h tends to 0. And it's going to be 0 plus h over 0 plus h. H and h will be cancelled out. It's going to be 1. So again, you can see that the left hand limit and the right hand limit are not equal. And therefore, limit x tends to 0 f of x does not exist. And let's see an interesting question, which is limit x tends to 3 This is a sign of greatest integer function. This sign is greatest integer function, and we have to determine whether the limit exists or not. Its greatest integer function, it means, for example, if I write inside the greatest integer function 2.6, I get 2. Okay, it's just its greatest integer just less than the number. So if I write here, let's say 3.2, then I'm going to get 3. If I write, let's say 2.9, then also I'm going to get 2. So the greatest integer just less than the given number. Okay. So first let's evaluate its left hand side, which is now here the limit h tends to 0, and this is going to be 3 minus h. Or otherwise we can write limit x tends to 3 from the left side. It's slightly less than 3, so it's not greater than 3 or equal to 3. So if it is less than 3, it means its greatest integer function will give us 2. And let's evaluate the right hand limit. So if it is, we are approaching x from the right side, then it means the greatest x inside the greatest integer function will approach to 3. And here you can see that the left hand limit is not equal to right hand limit, and therefore the greatest integer function at 3, the limit of greatest integer function at 3 does not exist.